Hey everybody, today we're looking at this idea of optimization. So really what we're going to do today is take these linear inequalities that we have been graphing and we're going to go ahead and put a little substance to them, meaning, what it would be like a real world type application of this. So the idea of what we're doing here with optimizing is trying to find a max or min for whatever it is that we're dealing with. And we often refer to this as linear programming because we're trying to optimize these functions, meaning we're going to come up with like a cost function or a profit function. So like I said, very real world type applications. And our goal is to either figure out the maximum or the minimum depending on the context. So if I'm a business, I would like to maximize my profit, yet minimize my cost. So depending on our type of functions that we're dealing with, we might be looking for our max or our minimum. And how we do this then is we go ahead and we use these inequalities, which we call constraints. So these would be like the limits of our operation, right? There's only so much storage space for inventory, or I only have so many hours I can pay workers, just due to the size of my building or the size of the market, whatever it is. And then the points contained in this graph is something that you heard me say the other day is called a feasible region. And really what that is ends up being the shaded area of our inequalities. So let's look a little bit about what we're trying to do. So once again, the idea here is to find this idea of an optimal solution, okay? So our minimum or maximum. And now what's also kind of neat about this is that it's also going to occur at a vertex of the feasible region. So meaning if I have a couple inequalities, right, our max or min is going to occur at one of the intersection points, okay? And then we say if the region is bounded, this minimum or maximum must occur. Well, what does that word bound mean? Okay, well, a bounded region is going to look something like this. So kind of just like the picture that I just drew, is that our region here, or our shaded area, has endings, right? So it's all contained, in this case, in a single triangle, which means my vertices are going to be my minimums, my maximums, okay? Now, what's the opposite of a bounded region? Well, the opposite of a bounded region is an unbounded region. And so here, if this was my shaded area, you can see that, right, it's going to keep going in one direction. So what that means is that these vertices will represent either a max or a minimum, but it can't be both because our shaded area keeps going. So technically, like down here at infinity, we'd have some other vertices, right? Which could be our maximum or our min. So when it's unbounded, we're going to have one or the other, but not both. Okay, so the next slide here talks a little bit about kind of where we're going to be headed. So eventually we're going to have to create these equations from a problem. The ones we're going to do today, it's going to be given to you. So we'll come back to this slide next time. So for now, here's what we have. So our problems today are going to look like this, where we have our constraints. So in other words, we have our inequalities that we're trying to graph. And the only thing that's new today is a subjective function. And this objective function is the one that we are trying to find the maximum or the minimum of, depending on our problem, right? So here we don't have any context other than just our equations. So we'll just list them both because those values don't mean anything to us right now. We don't know if this represents profit or cost or anything like that. So we go ahead and we graph our inequalities. And I'm going to go ahead here, since I got a big number like 8, I'm going to go by 2s on my graph. Okay, so our first one, we have x is greater than or equal to 0. Anytime we have x equals with no y's, it's going to be a vertical line at 0. So we have, or I should say a vertical line at that value of x. So we're bigger than 0, so it's going to be to the right. We also know that our y's are greater than or equal to 0. Anytime we have y equals a number, it's a horizontal line at that. So it's going to be up here. And then our last one here, x plus y is less than or equal to 8. Again, we could solve that to put it in slope-intercept form if we wanted. I'd subtract an x from both sides, so we'd be at 8, and then down 1 over 1, down 1 over 1, down 1 over 1, so on and so forth, and our graph would look like this, okay? Yeah, my line got a little bit off there. There we go, okay? So now we would be everything below this line, so that means our triangle here is our feasible region. So what we've done so far, that's not anything new. We're comfortable with that. Here's our new piece for today, is using our objective function to find our min or our max. So what we want to do is list the vertices or the corners of our shaded area. So this point right here would be at 0, 0. This point right here would be at 0, 8. And this one is at 8, 0. So those are the points of my vertices. So now to find my minimum or my maximum, I'm just going to take these values and I'm going to plug in my x and my y values to come up with my equation, right? So this is just our notation, meaning we're plugging in the ordered pair. And then here's where we do our work. So for the first one, we do, well, 3 times 0 plus 4 times 0 would just be 0, okay? Here we would have 3 times 0 plus 4 times 8, which would be 32. And this one here, again, we're taking 3 times our x value, so 3 times 8 plus 4 times 0 would be 24, okay? So now how do we answer our question? Well, which one is the smallest value? 0. So we could say we have a minimum of 0 at the point 0, 0. And then our maximum, well, our biggest value we got was 32, and that occurred at the point 0, 8. Let's do one more together. So here we have, again, a couple inequalities, all right? We have this right here. So this is saying that our x is between 2 and 5. So that means I'm going to have a vertical line at 2, vertical line at 5. That's what this represents. Now we have y is greater than or equal to 0. So I know I'm between 2 and 5, and I'm bigger than 0, which puts me in that range here. Lastly, we have this one here, so negative 2x plus 12. And I didn't adjust my stuff here, but if we were to plug in some points, maybe 2, this would put me at 8, right, which would be up here, okay? So I'd be down 2 over 1, down 2 over 1, down 2 over 1. So our line would end up looking something like this, okay? So our shaded area then is going to be our trapezoid looking thing here. So this ordered pair would be the ordered pair 2 and we said 8, right? This one right here would be at 5, 2. We have this one here would be at 5, 0. And this one here would be at 2, 0. Once again, we're using our objective function to find our minimum and our maximum. So we're just going to take our 4 points that we have. So 2, 0, 5, 0, 5, 2, and 2, 8, and plug those in to our objective function. So for this one here, right, we'd get negative 2 plus, well, 3 times 0 would be negative 2. We're plugging in 5, 0 here, so negative 5 plus, well, 0 would be negative 5. We would have negative 5 plus 3 times 2, which would be 6, so negative 5 plus 6 is 1. And here, we'd have negative 2 plus 3 times 8, so 24. 24 and negative 2 would be 22. So once again, how would we answer our question? Well, we have a minimum of negative 5 that occurs at the point 5, 0. And then we have a maximum of 22 that occurs at the point 2, 8. And that's what we're working on today.